In this session, let us see how we can use Cauchy criterion for series to figure out the convergence or divergence of a series. Now, we have already seen Cauchy criterion for series is the series converges if for every epsilon greater than 0, there exists m in n such that the absolute value of the tail series is less than epsilon for all n greater than or equal to m and all p in the set of natural numbers. So let's take an example and work through it. Remember this? Let's revisit this series. So here, important thing to note is that n goes from 0 to infinity, x to the power of n. So here, instead of 1, we could have also written x to the power of 0, x to the power of 1. So x to the power of 0 is 1, x to the power of 1 is x. So this is how the series is. Now, here, let's say u sub n is equal to x to the power of n, where n is in the set of natural numbers including 0. That's what this notation means. So henceforth, I'll be saying n sub naught. Okay, now if you recollect the previous discussion on this series, we had various cases. So let's take it case by case. So when x equal to 0, we get this series n equal to 0 to infinity of 0 to the power of n. Assuming here 0 to the power of 0 is equal to 1, which means u sub 0, that is the first term, is 1. For any n in n sub naught and any p in n, the series, absolute value of the series, or rather the tail series, is equal to 0 plus 0 plus 0 plus 0, which is equal to 0. Now, the moment I say tail series, you should understand that I'm not including 1 or any number of initial terms, a finite number of terms. Now take epsilon equal to 1. Then for every m in n sub naught, the absolute value of the tail series is equal to 0, which is less than or equal to epsilon for all n greater than or equal to m. So no matter how large m is chosen, the tail sum is smaller than epsilon for all n and all p. What does this mean, all n and all p? It doesn't matter what the value of n is and what the value of p is. The series, the tail series, that's why it's called a tail series. So u sub n plus 1 up to u sub n plus p, if we add it up and take the absolute value, it is less than epsilon, which we took it as 1. So for any m in n sub naught, the Cauchy condition for series is satisfied. Hence, the series converges. So here, the moment I make this statement and it is applicable to this particular context, that means Cauchy condition is satisfied, and which in turn implies that this series converges. Now let us look at the second case. Absolute value of x is less than 1. Of course, this means x is between -1 and 1. And here 0 is excluded because x equal to 0 we have already looked at. Now let's take the tail series. So absolute value of the tail series, and we split this absolute value. So this tail series will be less than or equal to the absolute value of x to the power of n plus 1 plus absolute value of x to the power of n plus 2 plus dot 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 plus absolute value of x to the power of n plus p. This comes from the rules of absolute values. Okay, so now here the RHS is a finite geometric sum, and we know the formula for a finite geometric sum. So this implies that absolute value of x to the power of n plus 1 times 1 minus absolute value of x to the power of p by 1 minus absolute value of x. Now what is this? This is a times 1 minus x to the power of number of terms divided by 1 minus x. So a is absolute value of x to the power of n plus 1 times 1 minus absolute value of x to the power of number of terms. How many terms are there? There are p number of terms divided by 1 minus absolute value of x. Now from this, if we take out 1 minus absolute value of x to the power of p, which is what we have done here, then this becomes less than or equal to this. Since absolute value of x is less than 1, we have absolute value of x to the power of n plus 1 goes to 0 as n goes to infinity. Therefore, given epsilon greater than 0, there exists m in n such that absolute value of x to the power of m plus 1 divided by 1 minus absolute value of x is less than epsilon. Now let's understand this a little bit more concretely for some specific value of x and for epsilon, and then figuring out what m should. So for example, if x equal to 1 by 3 and epsilon equal to 0.01, then we don't need absolute values because 1 by 3 is already positive. So 1 by 3 to the power of m plus 1 divided by 1 minus 1 by 3 is less than 0.01, which is 1 by 100, which implies 1 minus 1 by 3 is 2 by 3. We take it to the other side, we get 1 by 3 to the power of m plus 1 is less than 1 by 100 times 2 by 3. Simplifying that, we get 1 by 3 to the power of m plus 1 is less than 1 by 150. So now we have to figure out for what value of m this inequality holds. So let's put some values. So let's say m plus 1 is equal to 1. Then what happens? We get 1 by 3 is less than 1 by 150, which is not correct. Now let's say m plus 1 is equal to 2. We get 1 by 9 is less than 150. Again, false. M plus 1 equal to 3, which is 1 by 27 is less than 1 by 150. Again, false. What about m plus 1 equal to 4? We get 1 by 81 is less than 1 by 150. Again, false. And now, m plus 1 equal to 5, we get 1 by 243 is less than 1 by 150. Now, that is a true statement. So, we have found m such that this expression is less than the chosen epsilon. Now, m plus 1 equal to 5 implies what? That m is equal to 4. So, m is 4 here. Hence, for x equal to 1 by 3 and epsilon equal to 0.01, choosing m greater than or equal to 4 ensures that the Cauchy condition for series is satisfied. So, therefore, the series converges. See, this was just a concrete example. So, therefore, the series converges leads from this. Now, let's look at the case of magnitude of x equal to 1. That is x equal to plus 1 or minus 1. Now, the general terms are u sub n is equal to 1 to the power of n or u sub n is equal to minus 1 to the power of n. As limit n goes to infinity of 1 to the power of n is equal to 1, which is not equal to 0. And as limit n goes to infinity of minus 1 to the power of n goes to 1 if n is even, but to -1 if n is odd. So in this case, there is no limit. So in both cases, the series does not satisfy the necessary condition for convergence. That is, the limit should be 0 as n goes to infinity. Here it goes to a limit, but that is not 0. And here it doesn't. It just keeps oscillating between +1 and -1. Hence the series diverges, which means we do not need any other tests. So we don't really require Cauchy's criterion because the necessary condition for convergence itself is not being satisfied. Now the final case where magnitude of x is greater than 1. That means x is less than -1 or x is greater than 1. So we have this series. For any n in n sub naught, choose p equal to 1, which implies magnitude of the tail series is equal to u sub n plus 1, absolute value. Why? Since p we have taken as 1, only the first term of the tail series is taken. U sub n plus 1 absolute value is equal to absolute value of x to the power of n plus 1, because u sub n is equal to x to the power of n. Now let epsilon be equal to 1. Since absolute value of x is greater than 1, absolute value of x to the power of n plus 1 goes to infinity as n goes to infinity. Hence, for every m in n sub naught, there exists n greater than or equal to m such that the absolute value of x to the power of n plus 1 is greater than or equal to 1. Therefore, for some n greater than or equal to m and p equal to 1, absolute value of the tail series is equal to absolute value of x to the power of n plus 1 greater than or equal to epsilon. So the tail sum cannot be made smaller than epsilon, no matter how large m is chosen, which implies that the Cauchy criterion of series is not satisfied and hence the series diverges. So in conclusion, using the Cauchy criterion, the behavior of the geometric series, that is the infinite series x to the power of n, is completely determined by the size of x or absolute value of x. If absolute value of x is less than 1, all the finite tails of the series can be made arbitrarily small, so the Cauchy condition is satisfied and the series converges. If absolute value of x is greater than 1, the tails fail to become small. They grow without bound, so the Cauchy condition is not satisfied and the series diverges. If x equal to 0, the series converges. If absolute value of x equal to 1, the necessary condition itself fails and hence diverges. That was looking at the geometric series and proving the various cases using Cauchy criterion for series. Now, if you found this session helpful, please do like, share, and subscribe. Suggestions and comments are always welcome. Thanks for watching. See you in the next session. That's it for now. Bye.